This is the first of the series of video tutorials that I'm preparing for doing simple buckling analysis in the 3D Experience platform, which has the Abacus program as its FEA solver. I stick to simple geometry because I don't want to spend too much time on creating a complicated part. And we start with the linear buckling analysis, which is precisely the focus of this particular tutorial. Uh, Generally speaking, when we talk about buckling or we introduce it into our undergraduate curriculum, we concentrate on the Euler buckling problem, which can be any one of these, incidentally, depending on the geometry. Uh, and the source of the confusion in future meaning the uh, analysis that somebody may be doing with finite element packages, unbuckling, maybe because this is introduced as a single load being present. Okay, so uh, the particular problem that I'm going to be looking at is this one, which is the clamped fixed or clamped free end. But the issue of multiple loads being present is going to be discussed in tutorial 5, and I briefly refer to it towards the end of this tutorial. Okay, so for simplicity, as I mentioned, I will be using a bar which is 1,000 millimeter long. It's clamped at one end and it is free at the other end, and I will be using 10 B31 elements. Now, B31s are the three-dimensional uh, linear elements for beams, and the the fact that I'm using 10 of them, and this being 1,000 millimeter long, means each of them is 10 millimeters, incidentally. However, there's no reason to do this problem in 3D, so I would like to restrict it to motion in one plane, and which means that if you are using the Abacus program, you will be using B21, but 3D Experience does not have two-dimensional elements, so I still use B31, uh, but I restrict the motion of this vertical line so that it doesn't come off the plane and it doesn't rotate about the other two directions. That essentially turns the B31 into a B21 element. So a three-noded linear element, it will be converted into a two-noded linear element. The material property are standard steel, and the length is 1,000 millimeter. The radius, the cross section for simplicity is assumed to be a circle, radius 60 millimeter, and you can do based on the Euler buckling formula. Uh, if you do the calculation, you see that the theoretical uh, buckling load uh, under under linear assumptions, of course, of Euler is roughly 5 times 10 to the 6, of roughly 5 million Newton. Now, this is, of course, a conservative estimate because the buckling may be occurring well below this, okay? And that deals with this issue of tutorial 5 and 6, where we talk about the concept of imperfection, etc., or lateral load. Okay. Now, if we once we run this thing in 3D Experience, we get a table like that, and this is the first buckling load, which can be compared with the theoretical one, which was 5 point, I think, 0.03, something like that. Let's go back here for a second. 5.023 10 to the 6. Here it is 5.004. For all practical purposes, this is pretty much exactly the same thing that the Euler buckling prepared, and it's not surprising us. Now, what this thing incidentally means that when I do this problem as a buckling problem, I apply 1 Newton downward. This is a reference load. So whatever you get, these are multiplier. Whatever you get, you have to multiply it by 1n, and you're going to get it in newtons. Okay. So if this was hypothetically, let's say that this was 1 million Newton, the answer that comes out here will be 5.004. Okay. Now, in this tutorial, after I calculate this for you, I'll say, okay, so let's go ahead and take a static analysis and actually apply this load. What should we expect? Should we expect to see that the beam buckles? Okay, that's what this is saying. If I do a static analysis and I apply this load, which is the buckling load, as a compressive load, should I see a bowing of the beam? In other words, should I see that it actually buckles? The answer is no. Nothing will happen. You'll see that. And this deals to the tutorial 5 and 6, which says, okay, the problem is that these assumptions that I made in the either Euler buckling analysis, Euler formula, or in the finite element, will assume that this load, actual load, is applied perfectly at the centroid of that cross section, and there is no offset. There is no offset, and that is needs to be taken into consideration, because the possibility of this actual load having an offset means that maybe there's an additional moment here, or maybe there's a slight tap that we get to this beam, and there's a small lateral force. So to do a more meaningful analysis, one should apply some lateral load or some imperfection, introduce some imperfection into the model, and then run the analysis. So there's the actual load. There's a lateral load. This is all going to be done in the tutorial 4, 5, and 6. And the moral story, you will see that if you're dealing with this situation, it is possible to put these two loads in a single buckling analysis within the buckling step. Put these things. But the problem is, you'll see that in the next tutorial, that if you do that, you get unrealistic and meaningless numbers, which may be hard to interpret. Some of them may be okay, but some may not. Okay, so let's go ahead and do this problem. Very simple. I'm going to make a line here. So let's make a line. I am in part design, 3DEXPERIENCE part design, which is actually really CATIA V6. You click on it, you make a line and point and direction. So for the point, I'm going to make one, create a point, coordinate 0, 0, 0, which is way down here. Okay. And then I'm going to give a direction being Z. Okay. And 1,000 millimeters. 1,000 millimeters. There we are. Okay, there's my line. Zoom out. There's my line, 1,000 millimeter line. Now, because I'm doing beam analysis, I need an additional point here. It's called the orientation point. So what I'm going to do, I'm going to create another point. The actual location doesn't matter, but it cannot be on this line. So I'm going to take it offset, maybe, how about making it 200 to the left so I can see it. In the direction X, I'm going to make a coordinate 200. And if I don't like it, I'm going to come and change it. Okay, 200. There we go. So there is a point here which will be used to orient the cross section, because remember, if this is a circle, it doesn't matter. But if it's an I-beam or a rectangular section, then it does matter how it's oriented. The cross section is still the same, but orientation is important. Okay, let's leave it like this. We're going to apply material to this, so let's go ahead to tools. Here, a material. I'm going to create one. Sorry, create a material. It's a standard steel, so I'll call it steel. Um, Today is December 25, 2023, Christmas Day. All right. Okay. Give it a minute. Refresh. Okay, let me try it again because it looks like it didn't go through. So click on it. Steel, December 25, 2023. Say OK. Right here, steel, December 25. Oh, this is the one that I did. Well, the other one is here too. So let's go ahead with this second one that I did. Apply, close that, put it on the part. Oops, green check mark. And now we're going to go and put in our number. And all it is a Young's modulus pretty much. We are doing a static analysis, so we don't need a density, structural, uh, general, abacus multiphysics, mechanical, elasticity, elastic, and this is 200,000 MPa, 123 MPa, and Poisson ratio 0.3. Excuse me. Okay, so we're pretty much done here. Now we're going to go to mesh at this thing. So basically, we're going to go to structural model creation, MTFEM. Under the meshing, use the beam mesh. You select this. You put 100 millimeter, 100 millimeter long. There's 10 of them. That makes it a meter. And we say mesh. Okay. 10 elements. 10 elements are created here. Now we're going to do the cross-sectional properties. So on the properties, first we define a profile for this, profile for the beam profile. Now this is profile, I can call it circular, or I can call it beam profile 1. That's what it is default. Let me actually make this thing, call it circular. Circular. Just a second. Okay, circular, I'll call it R of 60 mm. 60 mm. That's the name of it. Okay. The type is circular right there. Shape is circular. Radius is 60 mm. And we say okay. Okay, we created the profile here. You can see it. It's in the tree. Now we're going to create a section. So expand this using the pull down menu. Beam section. That is the section that you want to define on this line. And for the profile, we need what I created, circular. Oh, this was misspelling. Circular, okay. And then notice that the geometry orientation, this is something that's needed. That point, I have to select it. Let me zoom out here. This point needs to be selected, otherwise I won't be able to close that, okay? So let me show you. Cancel this for a second, okay? So if I remove this, okay, then I need, in some of the software you won't even be able to close it, but this is if it's not circular. But here, oh, because it's circular, you don't need this orientation point. So if this cross section was not a circular, you may have to select this, but it doesn't matter. I will select it anyway. This may be unnecessary because it's circular for this particular shape, but I'll select it anyways. Okay. Now these are the local coordinate system. Blue is along the line. That's directions. This is direction 1, direction 2, and direction 3. So okay. So we say okay. All right, good. So as I said, this point may be unnecessary. Uh, it is unnecessary in this problem because the cross section is circular. You don't need an orientation point. But I'll just leave it the way it is. This was a bit of extra work. All right, so we have the this thing meshed, and we have the properties defined, cross-sectional properties defined right there. And let's go ahead and save this thing. All right, good. So now we're done here. We're going to go to the structural scenario creation. Remember, this is a buckling analysis. You can do it either here or in a more sophisticated or more expanded version of the scenario creation, which is called mechanical one. But I'm going to do it in structural scenario creation. Okay, let's give it a second. All right, so it's a structural problem that you want to do, and we want to use this finite element model that I created. Remember, I divided into 10 elements. That's good. It's here, right there. Say OK. All right, and now we're going to create our procedure. So click on the procedures tab here, and it's the buckling one that I want to do right there. Buckling step. You click on it. We're going to use the default subspace iteration, which is okay for small problems. And the number of eigenvalues that we're going to extract is 10. The number of buckling load that we're going to extract is 10. And that's where this table is coming from. Notice that I extracted 10. I will be extracting 10 eigenvalues. And this will leave it the way it is. If we get a message that you need more iteration, we come back and change it. I'm pretty sure this is okay. So we say okay. Now, let's apply our restraints here, first of all. Now, notice that as soon as I did that, this red exclamation mark turned into a green check mark, meaning the procedure is defined. So let's go to our boundary conditions, okay? So this bottom is, we know it's clamped, so we go here, we say, instead of saying clamp bottom, I say fixed displacement, all 6 degrees of freedom, this bottom point, okay, good. And in order to make the problem as two-dimensional instead of three-dimensional, only bending taking place about the x-axis, why don't I prevent this thing to move in the x direction? So let's go to the same icon, fixed displacement, that entire line, say do not move in the direction x. It does not come out of the plane. It moves only in the YZ plane, and rotations are exactly the opposite. So this basically turns the problem into a two-dimensional problem. The two-dimensional beam problem. Okay, very good. And now we're going to apply our dummy. Notice that by the way, what's happened here is a single step was created, buckling step right there. You can see that. And these displacements that I put in there are appearing here. You can see that. Okay. And the element type, incidentally, let's check it out. Double click on this element with B31. Okay, we don't have B2 here. You can see that. And the standard Hermite polynomial is right here, but we're using linear one. It's there. Oh, let me check something here. I read something at the bottom of that. Two-noded linear beam, yeah, two-noded linear beam element in space. But because of these restraints that I put it actually becomes in the plane, essentially. So now we're going to go to loading, apply a dummy reference load of 1 Newton down up there. So force at this top point in the direction Z -1. That is my dummy load of -1, or reference load of -1. Let's quickly save this thing and run it. Okay, let's go ahead and run this thing. Simulate. You can do a model check, scenario simulation check, and run. Let's actually do that quickly. It's a good idea in case there are obvious mistakes that are going to pop up here. Good. Simulation check. Not all issues are going to pop up when you do these, but some trivial, some uh, simple ones are going to show up. I don't anticipate any problems. It's a good idea to read these warning messages, but that's fine. It says that if you have, you know, buckling is not supported by this algorithm, which is fine. You don't need it. So simulate. Now this is where it's going to run and extract the first 10 frequencies. Not frequencies, buckling loads. The one of interest to us is the smallest one, which is the one on the very top. And I should be getting 5, unless I made a mistake, 5.004. 10 to the 6. I think that's what it was, right? Stable, yeah. It's done. Right here. And if I close that thing, you can see your buckling load is right there. This thing times 1 Newton. Incidentally, a couple of things I want to mention to you, and that is if you want to see the displacement, this is fine. Obviously, the biggest displacement, first buckling mode is going to go sideways, no problem. But you, so if you left double click on this, okay, this contour plot dialog box opens up, and under this tab which says rendering, if you go and select instead of the beam style line, you say profile, and then say apply. Notice that it shows you the beam with its cross section and also the mesh. I mean, if you don't want to see these 10 elements, you can say none, apply. But if you do want to see it, you just say mesh, apply, and there we are, okay? This is just for demonstration, for the visualization purpose. It really has not much value, okay? So we say, okay, if you don't want to see that, you can go and just get it out of the way. That's entirely up to you. But well, I'll just leave it the way it is for now. Now, what I want to show you that if we go and apply a compressive load of magnitude 5 million there, here downward, and say, okay, show me the deformation, you're not going to see the buckling mode. And that's really what this is saying. So what happens if we apply a load of 5 million downward? Will it compress? Will it show the buckling? The answer is you don't see that. So let's go ahead and try it. Let's go to the scenario, and we put another step here. Either I can delete this buckling, but it doesn't hurt me. I just leave it the way it is. You can delete it if you want. You can delete this thing, but I'll leave it the way it is. Okay. So I'm going to say uh, procedure, and that's going to be static step. For now, I'm going to leave this thing as default, except that for time step, for the initial time, I'll put down point 1, because otherwise you just see the whole thing in one step, which I don't want to do that. You say, okay, notice that the nonlinear geometry effect is on by default. We just leave it on. And here's the second step that's created, or static step 1 is created. Because the first step, was a buckling step, none of that information is actually transferred, like the boundary condition and things like that are not gone into this. Okay, that's because the first one was buckling. So let's see now. We go up here, see if we can force it. We say this thing also step in. Okay, so let's do the following. Right click, uh, feature manager, and you can see that these things, for example, these conditions are not transferred into that. So what we can do is we can actually say it looks like we have to see, you cannot take this thing and say start in step 2, because it's a buckling step, because right here, see that there is no start in step 2. So unfortunately, I have to do this thing again. So let's go ahead and do that. I'm gonna, what's this? Okay, so I'm gonna go to boundary conditions. Why don't I hide these things actually? Why don't I hide this whole thing so you don't see it? So we go to boundary conditions. This was fixed. This bottom point was fixed, right? Okay. Okay, and then we eliminated the motion of this thing in the x plane, in the x direction. So we do another one. That entire line, no motion in x direction, and rotations in the opposite coordinates are fixed. Okay, good. And now this load, we're going to apply load here. This is the load from the previous step. So if I, in fact, if I hide this thing, if I hide this, where's that load? Right here. I can hide this. You don't see it. It was easier probably if I sorry, if I deleted that buckling step, but that's okay. Let me hide this. Okay, good, good. So we go under load, on that top point, the force on that top point, okay, in the direction Z, negative 5.004 e to the 6, which means 5 million uh, newtons. There we are. Now remember, this is different from that. Force 1 was 1 newton, and it's going to be used only in the buckling step, okay? And you know, if the force, and it's not even showing because I hit it, okay? The one that I just put in there is right there, and it's going to go through the static step 1. The alternative would have been, instead of deleting this thing, to deactivate this whole step, okay, if you didn't want it. But that's okay, that is not the issue here. So let's go ahead and run it. So let's go ahead and run it. It's going to run the buckling step again, which is totally unnecessary. That's why deactivating this would have been better. Okay, I just want the analysis of that portion. Okay, but because this is not deactivated and it's not deleted, it's going to do this one too. Okay, so let's go ahead and do it. And all we're going to see is the compression. We're going to see is the compression of that bar. No buckling at all. So the bar has no idea this was the buckling load. That has to be done a different way. That is going to be done in tutorial 6. And I want to show you, by the way, that both steps are done again. If you go to, let me just wait for a second. If you go here, let me close that. Notice that there's a buckling step 1, which was done, okay? And there is the static step. This base step is essentially the initial situation, okay, base step. Obviously no displacement. So buckling is this, which I'm not interested, but I told you that it's going to be done again because it was part of this whole tree. It was not deactivated or deleted. And now if you want to see the compression, you go to static step 1, right there. This is the initial, and then notice that it just compresses. It just compresses. We went all the way to the buckling load, but it doesn't see any sign of buckling. Okay, so we're going to come back to this issue in tutorial 5. All right, we'll see that. And let me quickly remind you why this is happening is because we are dealing with the ideal situation. This is, there's no offset, there's no eccentricity between this load applied and the center line here. Okay, there's no lateral load, so it just tries to compress it. If we want this thing to show buckling, okay, buckling, we have to do, as you will see later on, we have to apply a lateral load. That's one way of doing it, and then do a nonlinear analysis. We'll come back to that later. Good luck.